What we're looking at here, we've just we're going to use this model, right? So look at this. Okay, so effectively what I have here is I have a silicon, and I have the 8 electrons here. Okay, 8 electrons, right? We've a key here. Okay, the light brown are electrons, and the dark brown will be protons. Okay, or positive charges, which we look at in a minute. Okay, that's just to give us an idea. Right. So let's get clear on the three scenarios. Okay, silicon, 8 electrons, all tightly bound. Very occasionally one of those electrons will escape, okay, and we have an electron that's free to move, and we have a gap left here called a hole that's free to move. That's intrinsic conduction, as we said. Okay, we remove that, okay, and go to phosphorus. Right, phosphorus, instead of having the 1, 2, 3, 4 electrons from here and the 4 with the sharing silicons, we have an extra electron. Oops, wrong color. Okay, we have the extra electron. Okay, so we have this electron which is now free to move. So there are extra electrons. These are the electrons are majority charge carriers. It's due to doping, so it's called extrinsic conduction. And finally, the electrons are the majority charge carriers. There are still some holes as minority charge carriers from the pure semiconductor. Finally, if we replace the phosphorus with boron, okay, right, we're short 1 electron, so we've got this extra hole as the charge carrier. So again, it's extrinsic conduction, doping through current flowing through a doped semiconductor. It is p-type semiconductor because we've added a neutral boron to the Newton silicon, so it's not positively charged, but we've extra plus charges, these called holes, and therefore we call it p-type semiconductor. Right? Now finally, let's look at where this idea of a hole being negatively charged comes from. So let's look at this, and this is very important, right? Okay, so let's take an electron. Okay, I have an electron here, okay, and look, I have a negative charge connected to this side and a positive charge connected to this side. So because the electron is negative, it's going to go from right to left. It's going to go across here. Okay? So negative charges are going to the left. If I take a positive charge, doesn't matter what the positive charge is, this guy, okay, this is positive, it's going to be attracted to negative, so positive charges go to the right. So it's pretty obvious. Negative goes to the left, positive goes to the right. But let's take this scenario, and this is the scenario that you're going to have in a semiconductor. Okay, these are all electrons in the bonds, but there is a hole free, 1 hole free here. Okay, now if you connect a plus and a minus here, watch what happens. Now I want you to watch the hole. Watch the hole. Okay, the electron, this electron goes in here. The hole is moved to the right. This electron goes here, the hole has moved to the right. This electron goes here, the hole has moved to the right. So the 3 electrons move to the left, but it's the same as seeing 1 hole moving to the right. Let's do it again. It's almost like magic. Okay, so watch the hole. Forget about the electrons, watch the hole. Okay, watch the hole. So we're going to start it. Did you watch the hole? The hole moved to the right. Now let's go back. We said, watch, electrons move to the left, negative charges move to the left, and we said plus charges will move to the right. So, what is a hole? The hole is a positive charge. It's called a positive hole. Interesting stuff, interesting stuff.